All right. Okay, so the big thing is that ideally we've been minorly exposed to what a differential equation is, right? But it's basically, it contains derivatives, and it's not just in the equality of the variable we're derivating with respect to, but it's usually with the variable we're derivating of. That's what really separates the differential equation, right? So dy dx, the y part is in the equation. That's what creates, all right, a differential equation and actually separates it out. So again, we're starting with the simplest example, right? F equals ma, all right? And I could put in either the first derivative, all right, or of velocity, or the second derivative of position. And then I can create myself two differential equations. And so this function, this is what I'm identifying, the function of time and position, all right? This equation over here has both of these variables included. Having time, that one we're super familiar with, but then having position, right? Having the variable that we're usually differentiating, that's the new part. And that's what creates, all right, a different approach to solving derivatives than we have been very used to all along, right? Implicit differentiation and all that, right? We have to go beyond that. But that's basically what a differential equation is, all right? We have both the variables, but specifically the variable we are differentiating. Now, there are two levels: ordinary differential equations represented as ODEs and partial differential equations represented as PDEs. This class is specifically about ODEs, ordinary differential equations, which reminds me, I just had a student that graduated last year. They made him take DFQ again, but luckily you're going to school, so actually it won't matter. And their differential equation class was half ODE, half PD, and this one didn't count for it because he went to like a school in Minnesota. So I was like, you're going to South Dakota school, so you should be fine. But just so you know, Josh,
might be taking this class again.
Half of it will be familiar, half of it would be new.
That's not a big deal. Okay.
So kind of depends what you want to do next.
Yep.
I was like, but yeah, he was trying to fight it and they denied him.
I don't blame him. It's 2 classes.
Okay. Also, what we're going to focus on, because they're the most common type, is linear differential equations. All right, linear differential equations, right? We have lots of powers, all right, all the way up. And one of the biggest parts that we are going to look at is this equation on the other side. Notice this is just with respect to t, the variable we are differentiating with respect to. We do that because it makes the solving of the differential equation simpler. If you can get all the other variable to one side. And luckily, this is the most commonly occurring system, right, that occurs in systems we will reference. Nonlinear, we're going to solve some of those as well. All right, they become more complicated, but we'll see some things. We'll see some situations to approach those as well. All right, so a few examples, and let's identify if these are ODEs, PDEs, all right, and the order. So the order is just the power of the derivative. Yeah, so the order is just the largest derivative present in the differential equation. All right, so for A, this is our standard example, all right, of a linear differential equation. All right, we don't have any variables of our function y, which is the variable that we are differentiating. All right, this is a second order, since we have a second derivative, right? And this is an ordinary differential equation because there's no partial derivatives. And it is that simple to identify. We can look at this list pretty quick. Which one is a PD?
Delta.
D. I mean, A through H.
D, yeah.
Yes. D and F, right? Because, oh, look, there's partial derivatives in those, right? So I can identify those pretty quick. Also referencing other notation, do you recognize any other PDE notation?
The double X.
Yeah, so E actually also. Right, so we jump between all these notations, right? So just remembering some of our Calc 3 there. Okay, all right, back to B. All right, so this is clearly an ODE. All right, and this guy, all right, here's the big order. All right, this is a second order. Once again. And then linear is about the variable of the function within. Okay, so B is nonlinear for several reasons, actually. Okay, one reason, okay, e to the 5y, I have the variable, all right, that we are differentiating in the exponent, all right, that's also bad. This guy, sine of y, right? That's nonlinear as well, right? Periodic. Also, that's y squared. As soon as you get past first powers, notice that this, we have a derivative, okay? But a, b, and c are just constants, all right? And this is a function of t. So this, all right, has several reasons that this was nonlinear. Okay. C, clearly ODE. What order is it?
Third. Fourth.
Fourth order.
Sorry.
And then is this linear or nonlinear?
Linear.
Nonlinear, why?
Because it equals cosine, which is
Important. Cosine of?
T. Oh, it's a different variable than
That's
actually.
the variable we are differentiating with respect to. So that one's actually okay. This thing can be a mess. We want to focus on our y's. Oh, that's a derivative. So that's a derivative. That's a derivative. That's just for.
So linear.
So it is linear. Yes. And so that's the trick of these. Notice this one, right? And that's why I started with this one. This one said G of T. This could have all kinds of mess with T. T doesn't matter. It's the Y, all right? That matters. Or okay. Let's see. This guy. This actually probably is linear. Once you identify PDE, okay, that's linear. And then what order is this? Second order, yeah. Yeah, see, this one I can't even tell. The second derivative,
Echo.
that is the function. Yeah, that should still be linear. Assuming, yeah, a squared is just variable. And then what order is that? Second order as well. And then lastly, PDE, what order is this? Third order.
Linear.
And it should be linear. It's not much here, but the derivatives. All right. And then, okay, so ODE or PDE? ODE. What order?
First order.
First order.
Linear. Actually, no, non-linear because the derivative equals a power.
So 1/3 power, what does 1/3 power mean? It's radical, right? This is actually, yeah, radical of y. So yeah, non-linear.
And the same thing with the next one.
Yeah, same thing with
Just
this.
ODE, second order, non-linear.
What order?
Second? No, first because it's a derivative is the y prime.
But you're absolutely correct. No, linear. So we just want to identify just some of our nomenclature here. So now most of what we do in DVQ is solve our differential equations, okay? But just to start with, we have a solution of this differential equation, and I want to prove it the other way. So I have the equation, and notice that as we get better, we kind of drop this notation. Sometimes we keep it because we start having too many variables. Y of x equals x to the -3/2. So in order to prove that is a solution, I have the function y. What do you think I need to do if I have this differential equation?
Like actually plug it in and solve it, like do the derivatives and plug it into the equation.
Exactly. Take the derivatives, right? We're just going to take a couple of derivatives and then plug that into the equation and make sure 0 equals 0. So now again, usually, like I said, we start with this piece and find that. But just to make sure we're up to task. And then one other big thing, and what's known as intervals of validity, and we're going to get into this pretty heavily, okay? Solutions to differential equations are always on an interval. So when you get the solution or the differential equation, you identify the interval of validity, and that's going to be a big thing, all right, that we're doing. All right, so why? Let's keep it one. Prime of x equals -3/2 x to the -5/2, and double prime. What am I at? 15/4. So we take a couple derivatives, and then we can plug all that in. And basically, we're just trying to identify, and we would see, leave the proof to the reader. But basically, we would see, all right, we're verifying, all of that will cancel out with some fun algebra. And here's the big part. There are many possible solutions. These vary on what their particular intervals of validity could be, but we're going to identify that there are many possible actual solutions with usually one overall general solution. Put this one. So there are many possible solutions. And here's the other thing. Notice these last two solutions. There's even you can create a combo of those two solutions, all right, that is a solution as well. Each of these individual solutions are what are known as actual solutions created, what we're going to talk about next, from initial conditions. Because initial conditions, all right, identify a specific set of conditions that the differential equation can be solved for, and also referred to as initial value problems or IVPs. This you should be the most familiar with because we touch on this in Calc 1, Calc 2, and Calc 3, all right, solving the simplest levels of IVPs. We're going to go much more in depth, all right, into IVP equations. But you have some initial condition, right, for a particular X and Y value, or T and Y, or whatever you want to call it, all right? And then you can solve that equation down. For our problem that we just had, we have this differential equation. So we would additionally be given information, right? We would say, solve the initial value problem of this differential equation, where y of 4 equals 1/8, and y prime of 4 equals negative 3/64. So you have additional information. Important, in order to be able to solve the IVP, whatever the order of the problem is, right, you will need that many initial conditions, right? Second order, that means I have 2 initial conditions because you have to have the derivatives lower than that and the one without the derivative, just the algebraic function. So given we already have the solution, because again, we already have this. I can then plug in my initial conditions. And we can verify that this solution satisfies those conditions. Notice, so all those other solutions we have, they would not satisfy. So even though there are many possible solutions, only this solution satisfies these particular initial conditions. Now again, I know this is weird because we're doing this backwards. I was like, we already have the solution. Most of our work comes from identifying this. Okay, but this case again, we're just doing general overview of differentiation. As I said, actual solutions, that is specific solutions to initial conditions, all right, that's what we find a lot. Those are the solutions to IVPs. The general solution satisfies the entire differential equation, all right, but is not nearly as specific. Hence, that's why it's called the general solution. Depending upon what kind of problem we're solving, we'll bounce back and forth between finding the actual solution, all right, and the general solution. Once you have the general solution, though, finding the actual solution is very, very quick. So we have this general solution, all right, to this differential equation. All right, and again, it's written in terms of C, just like remember when we integrate plus C all the time. So what is the actual solution to the following IVP? All right, where y of 1 equals negative 4. So if I have my general solution here, and then, right, I have t equals 1, y equals negative 4, I can solve this down to find myself C and get the actual solution. Negative 3 1/4 and 4 3/4. That's the function. Oh, I didn't even bother. Okay, writing a decimal in a fraction is absolutely horrific, but you guys get it wrong. So the whole idea is that once you find the general solution, and a lot of what we do is finding this general solution, plugging in the IVP conditions to solve for C, K, and however many additional constants we're going to have, right, should be relatively quick.
Is it okay if we mix decimal and fractional stuff in our answers? Or do you want that as,
It depends on the situation. This one, it doesn't really.
I guess 19/4 would be.
Oh, yeah, I would much rather, I was like, I just didn't, I was like, I didn't want it.
Not even if you want to do 19/4 squared. I just didn't know what you wanted on the tests or what you wanted on your.
Oh, I mean, I'm looking for concepts most
Yes,
of the
sir.
time. So I was like, I don't have a preference whether you,
Okay.
sometimes I go straight to decimal and we're gonna get into the problems where it's really nitty gritty and they don't come out as fractions.
Yes, sir.
You know, like, so I was like, it depends on the situation.
Okay.
I mean, whenever possible, be exact.
Yes, sir.
Okay, so implicit and explicit. So notice, right? Okay, we have explicit solution here. Whenever possible, we're going to solve it explicitly. We're going to see plenty of cases where we cannot solve it in explicit form. So, I mean, we're going to have to make sure we're just as clear as possible when that occurs. All right, so as promised, the big thing is that a differential equation represents a direction field. Without a doubt, one of the biggest applications of DPQ, all right, is to physics. So we're going to start with our classic situation, simple falling object. The two main forces on a simple falling object, okay? We have gravity and resistance. Force due to gravity, we can write as mass times gravity. The air resistance, since we are going to, one of our big things is how you set up your axes. In this case, given that the force of gravity is mg and the force of the resistance is negative gamma, which are just representing any proportional resistance to the velocity. What direction is my axis here? Which way is the positive axis specifically?
Going down.
Yeah. I was like, just for fun. Whether you do it the other way, okay?
It's a matter of perspective, right?
Yeah. Don't care. Always works. Of course it will. All right. I just set it up like this. So often down being positive makes our problems easy. All right. But does it work the other way? Of course it does. So back to what we originally started with. Our equation, all right, second law of motion, right, ma equals F. When we set this up as a differential equation, now I can actually put my pieces in. So my ma over here, which I'm using dV/dt, so we're just looking at velocity. Since I have air resistance written as a proportional velocity, right, gamma some value. Notice that I have a differential equation because we're differentiating velocity with respect to time. So mass constant, gravity constant, gamma is a constant, v. That's what we are differentiating, and it is in our equation. That's what has created, all right, our differential equation. Divide the whole thing by m, all right, just to write it explicitly as dV/dt. And then I just grabbed some values. Now I know, all right, gravity is not just 9.8, but it's actually
9.06, whatever.
9.81.
Yeah, 8.1's
like,
most accept is 8.1.
Yeah. I was like 9.8. I was like close enough, right? Yeah.
For government work.
So I picked a mass, 2 kilograms. All right. I have the proportional values. And I did all that just so we could create, all right, our differential equation with actual values. All right, dV/dt equals 9.8 minus 0.196 v. This is now a complete differential equation. Fine. So we don't have the constants anymore. All right, we have a variable that we are differentiating, variable we are differentiating with respect to, but notice it's not even in the rest of the equation. All right, and then that is what we can plot. Now, be aware. Could I go through and plot each of these individually? Absolutely. All right. Pick a t value, all right, because t values are x values. So pick a t equals 1. All right, you plug it in, all right, you get a value, and then you can do that an infinite number of times. Very fun.
When we're doing these, we have to do units and unit counseling, or is that not important and not an important thing in this class?
No, because our units are always going to work out. And this is the directional field, right? We need to know, right? What are we talking about? What are the units of velocity?
Meters per second. Well, typically distance per time.
Yes, in this case, right? In this case, I was like distance per time. So usually we worry about our units.
Yes, sir.
I was like, trying to think if there's going to be a case where we might have to keep track a little bit closer.
Because like, you're doing derivatives and stuff of units, you have to kind of keep track of that too, or else you'll kick a loss in the sauce.
I was like, usually at the end, we should be able to figure out what we have. But the dimensional analysis, we're not going to worry about heavily.
Okay.
So, all right, the whole idea of a directional field is that based on particular initial velocities, okay, we can identify what is happening and where it's approaching, right? Its terminal velocity, which, all right, will always be the horizontal tangent of the derivative, which means all I have to do is do what with this equation?
You get 0.
Set it equal to 0. I could set this equation equal to 0, solve this down, and I will get a velocity of 50 meters per second. So I can verify that algebraically, but looking at the directional field. Guys see the horizontal direction? Or the horizontal tangent line?
Right at 50.
Right at 50.
As if it works.
The algebra verifies, right, with the plot. And this is what we're going to do in GeoGebra, right? I'm going to show us how to do this in just the big thing we're going to identify is long-term behavior. So notice that regardless of initial velocities, what are all these headed towards?
50.
50, all right? The ones that start below 50 are trending upwards. The ones that start above 50 trend down, right? So hence the terminal velocity of 50 meters per second. So long-term behavior of directional fields, that's the biggest thing based on initial starting values, all right? Regardless of what happened here, whether the initial velocity was 0 to infinity, all right, they all trend towards a velocity of 50 meters per second. So you can graph these, and this is what GeoGebra does really nice too, right? You can pick a bunch of these because this is the simplest case, right? It's just one, all right? But when you have multiple, all right, horizontal direction fields, some trend up, down, and so we really have to mess with it. But this line, all right, well, we could plot that in, and it's so helpful. So the solution of curves, right? Very, very nice. And so GeoGebra. Okay. So all you have to do, right? And I had it in the notes there, right? So I have the link in there, but all you have to do is just Google GeoGebra scope field plotter. That's the fastest way that I do it. So it's not called a direction field plotter, it's scope field plotter. Okay. So, all right, we're going to type in our equation and notice, all right, so it's got, all right, the explicitly solved derivative of, over on the left side. Then we can put in our equation. And this is way better on a computer than it is on the iPad. Now, the toughest part of these actually is identifying your range, because it always starts -5 to 5, which is super annoying. So this is why we want to do some of the algebra first and have a basic understanding of our problem. But notice this is basically the same graph that we had drawn there. And here's what's really nice. So these over here. So you can drag those around. And so when we start getting more annoying ones, right, you can drag them around and identify, oh, here's a horizontal, here's a horizontal, here's a horizontal. But we solve that usually with our algebra because that helps us. The big, like I said, the toughest part is identifying this range. Once you have at least an idea of what the range should be, right, doing the rest of this actually is pretty quick. All right, are we okay with the?
My computer's re-updating, so
Oh,
I
okay.
think it's a different day. So
But I mean, it's not, it was like, it's pretty straightforward, right? I mean, and notice, with the, once again, government work, it's kind of heavy on the rounding. I was like,
we'll always do that then.
but this is free software, so I was like, if you go ahead and purchase Maple, it's like $200. It's like,
Is that for a year? Or is that just,
I think that's the year.
that's steep.
Oh, yeah. Well, that's why the guys who made Maple actually created, Wolfram.
I was gonna say Wolfram Alpha, I didn't know that.
Wolfram Alpha, because.
That was free.
Yes, because they were like, Maple's getting too expensive, so they created Wolfram Alpha.
That's cool.
Lane, are you okay? Okay, so initial velocities where the vector field's positive, negative, right? So we can write this couple ways. So based on that graph, it really only breaks down into three pieces, right? Now, the long-term behavior of all of them is going to be the same. So if I was just doing long-term behavior, I would write this even more condensed. But since I want to do the vector field slope, right? Because long-term behavior, what's everything headed towards? Yeah. They're all headed towards the 50 meters per second. But the slope was actually different in the cases.
Is convergence not the right term here?
It is convergence.
I just want to make sure I wasn't being.
No, you're absolutely correct. They all converge.
Okay.
I was like to 50. I was like, and that's why I really would have written this as negative infinity to positive infinity of initial value. But because the slopes are actually different, that's why I broke this up, right? So we saw. Because down here, right, from negative infinity up to 50, what's the slope of the vector field?
Repeat that again, please, sir.
From negative infinity up to 50, what's the slope of the vector field? Right.
Is it 25.2? I can't.
No, not the exact number, just positive, negative, or horizontal?
It's going to be, well, okay. Positive.
Positive, yeah. It was like you were thinking it.
Yeah,
I was like, the line is going up.
And to the right.
Yes, but they're always going to be headed.
That's fair. Okay,
I was like, because long-term behavior, what's happening at infinity down here?
okay.
I was like, so they're always going to be headed that way. I was like, so yes, it's positive. At 50, it's
0.
horizontal slopes. All right, and then from 50 to infinity,
Negative.
negative. Right? That's all we're looking for. Yeah. Not the exact. Yes, to find the exact slope, I would have to look at this one specifically.
Yep.
Plug in those points and then see is that like, because that's, let's say that's 20, right? That's 20 over 1. Oh, what's this one? Oh, that's a little bit, I mean, that's a 5 or something, right? Yes. Know exactly what the slope is, you're correct. I just want us to identify positive, negative, or horizontal because
Okay,
yes, you're absolutely correct. I could find exactly what that slope is, but it's a nightmare. That's tedious. That's what we're not.
okay.
Yes, sorry. It's a vector field, positive, negative, horizontal. That's all we're. Okay, so this one is positive. This is horizontal. And this is negative. You're absolutely correct. We could find the exact ones, but that's not the point. We care about long-term behavior and then just want to identify, oh, okay, it's positive here, horizontal. And it's really just to identify the horizontal piece, because that usually has some indicator regarding our long-term behavior. All right, let's do a few more of those, all right, and practice with GeoGebra. I want to sketch the direction field, all right, for the following differential equation that we have here. Now notice, just as a note, we're differentiating y. What are we differentiating y with respect to? It doesn't actually say here, all right? So, oh, it doesn't say there either. I thought that was a t. All right, so t or x, it doesn't matter. So just so you know, this is very common how differential equations are written, and it doesn't matter if you pick t or x, okay? It's all the same. But this is just very, very common notation. The big thing that identifies this is a differential equation is I have the variable I'm differentiating on the other side, right? It's within the equation. That's what makes a differential equation. So let's determine how the solutions behave in the long term and if that's dependent on the initial value, and usually it is. In order to help us, all right, before we go running into GeoGebra, because I could plug this in immediately, all right? I want to identify what ideally are some of the initial values, which means set the derivative equal to 0. Identifying those horizontal lines gives us a big step up, right? Because again, spending your time doing those initial ranges is what takes all the time. And then I have, again, world's easiest algebra problem. Now here's the big thing. It's so funny, I tell people all the time, differential equation, right? We're doing this after Calc 3, and we're gonna see a few tough integrals, but most of differential equation, most of DPQs, we solve with algebra, right? Now we're gonna see some messy algebra, but we solve a lot of it with algebra. As far as the calculus we need, U sub and integration by parts covers 90% of what we do. All right. So algebra is everything. And as we reach the end of your math careers, it's so important that your algebra is just top tier. Okay. Because I was like, that's what everyone gets in trouble with. It's not the calculus, it's the algebra. All right. Okay. All right. So I got a nice one. How do I take care of that quadratic there?
Break it apart.
Break it apart specifically.
Y minus 2, y plus 1. So we'll get zeros when y is 2, y is negative 1, y is 1.
That is absolutely correct. So we have these, right, are the most helpful because these are going to be our horizontals. And likely, that's where a lot of things are going to be convergent. Okay, so just some initial stuff to help us, and then we can actually plug this guy in. Okay. I was like, on the iPad, this sucks so much.
Oh, I bet.
Okay. The most helpful part, without a doubt, all right, is grabbing these, and then they can definitely help us identify. So since we know, right, we had what, -1, 1, 2, something like that. We can see, all right, at least where a lot of the initial, the end behavior should be approaching. -2, was it -2? What was our low value? -1?
-1, yes, sir.
-1. Okay, so we can see right here at -1. Is that 1 or -1?
It's not going negative. I guess it's on the back axis, but not down the Y.
Oh,
Gotta change your Y bounds.
there we go. Yes, we gotta have negative in there. Okay, there we go, -1. So in order to identify, and then be aware, it does this. Obviously, it's not actually passing through the horizontal asymptote. So if you move, that's the flaw of GeoGebra there. So if it like does crazy stuff, again, just note that we're looking for what the end behavior is. And so the best way to always do this, since we have -1, 1, 2, all right, we can see our horizontal asymptotes. Then we just start, all right, given our initial values, start at -infinity and see what's happening. So -infinity all the way until -1, it's approaching. The end behavior is -1. But it actually goes beyond that because it's -infinity all the way to what value?
-1.
Not just -1.
Oh, up to 0 and to 1.
up to 1, right? Because everything actually below 1 all trends towards -1. And so that's what this is helpful for, because these slopes are positive, these are all negative. So everything from -infinity to 1, any initial value in there, will trend towards negative. And then, all right, so at 1, all right, what values trend towards 1? Range of values.
1, 2.
1 to 2. Initial starting values of 1 to 2 head towards 1. And then
Anything greater than 2 goes to 2. No, anything greater than 2 goes on.
yeah, it trends towards what number?
Infinity?
Infinity, yeah. Now, be aware we have to make sure we include everything. Okay, so 1 included to 2 excluded trends towards 1. All right, everything above 2 heads towards infinity. What did I leave out? It was hard to maybe when we write it, you'll see. Okay, so -infinity, all right, to 1. We just identified 1 including to 2. That all heads towards.
Then 2 to infinity.
And then all initial values greater than 2 and towards infinity. What are we missing?
Where's the horizontal?
No, nothing. Heads towards infinity. What number am I missing over here? What number is excluded?
-1.
No, I got -1.
That's on the right side.
-1 is in between these.
Yeah.
2. Don't forget exactly 2, because notice less
Oh,
than
I
2,
see.
greater than 2.
No, okay.
Y of 0 exactly equals to 2. It's the only one that heads towards what number?
2.
2. Ah,
Okay.
because it is a horizontal, right?
I see.
We identified our 3 horizontals, okay? One thing is definitely going to head towards each of those at minimum. There may be more numbers, initial values, but there's always going to be at least one. Because even let's say if everything below -1, all right, headed towards infinity and above, at least -1 is going to end up towards -1. It just ends out more than that just -1 initial value heads towards -1 in the long term. But all of them, all right, with 3 horizontal asymptotes, there's only 5 total possibilities, right? They're good. One thing at least is going to head towards those 3. And then what else could you have? We have one of them here.
It'll go towards something
Either
else.
infinity or -infinity. Now notice we don't have a -infinity because maximum 5. Minimum 3, maximum 5, right? It's always just going to be add 2. So if you don't have your horizontal asymptotes, something has to head towards each of those. It just, our trick will be identifying how much heads towards them. Is everyone okay lining this up with the scope field plotter? All right, and notice this one. Okay, so sketch the direction field for the following EVQ. This one is a fun one for a whole different reason.
Are we getting this? Is that what you guys are?
Okay, just making sure, so we're okay with the.
So, what's the long-term behavior of this one?
It's going to infinity.
Negative.
Negative infinity, yeah. But, well, actually, you're both correct.
Yeah.
I was like, but here's the real thing. Given what initial starting values? Back up. Where did we start? What did we find first on the last one? What was the very first thing we did?
Where it equals 0.
So what kind of asymptote is that?
Horizontal.
Horizontal.
Horizontal asymptote. What do you see here?
There is no horizontal asymptote.
Ah, what kind of asymptote is there?
Or what's the diagonal? I'm not sure what it's called.
Yeah, slant. It's called a slant.
Or oblique, you're absolutely correct.
Yeah, there's a slant somewhere around here-ish. Right?
I was like, but does that mean, I have no idea what, given the initial starting values, because it doesn't line up this direction. So sometimes all you can do is identify what's the long-term behavior here.
Well, I see a slant asymptote. Can't even guess what it would be. All right, y equals x plus 1, something like that. Just random guess,
Okay, because it's about here-ish. Okay, so, right, but it might have a steeper slope, right? And then I see that it's either headed towards negative infinity or positive infinity. That's all I can say here. So just again, I was like, making a picture is super important, but also knowing we always found the horizontal asymptote, but notice y equals x. When I solve that equal to 0, I get y equals x. I'm pretty sure that there's not the horizontal asymptote there at y equals x. So again, sometimes make the picture. Pictures are worth 1,000 words, and then just identify and say what we can. And that would be it. All right. So again, just kind of fun stuff. And a lot of this occurs, and we're going to investigate all variations. So just pay attention. I was like, not everything is our rules, right? We want to be outside the box. All right, yeah. So let's see. Just something else. Slant asymptote. At y equals x plus 1-ish. Long term.
Would you want to say like if considering the field left of the oblique asymptote
Like, or above.
or
Yeah,
above, it's
yeah.
going to approach positive infinity.
Yep.
If it's
That's basically what I was going to say. I was
right,
like, if it's above the slant asymptote, it's going towards positive infinity. If it's below. Yeah, I mean, there's no other way to say that. That's about as good as we can get from that situation.